So we'll be solving question number 5 from the book Challenges and Thrills of Pre-College Mathematics. So question number 5 says that Bn is defined as B1 equal to 1 and Bn is equal to An plus 1 plus An minus 1 for all n greater than or equal to 2, where An is the Fibonacci sequence. For the problems on An, you can check question number 4. So the first part for question number 5 is that we have to prove that Bn is equal to Bn minus 1 plus Bn minus 2 for all n greater than or equal to 3. So for this, we'll mainly use the recurrence from the Fibonacci sequence, that is um, An is equal to An minus 1 plus An minus 2. This is the main equation that we'll be using. So from this, we can say that um, An minus 1 is equal to An minus 2 plus An minus 3, right? Let's call this equation number 1. And then we can also say that An plus 1 is equal to An plus An minus 1. Call this equation number 2. Then we add both equation number 1 and 2. So what we get is An minus 1 plus An plus 1 properly is equal to An minus 2 plus An minus 3 plus An plus An minus 1, right? But we also know that Bn is equal to N minus 1 plus An plus 1. That's how we define Bn over here, right? So applying that on the left hand side, we get Bn, right? Because An minus 1 and An plus 1. And the right hand side, what we can do is we can club An and An minus 2, and we can club An minus 3 and An minus 1. So when we club An and An minus 2, we get Bn minus 1 plus, when we club An minus 3 and An minus 1, we get Bn minus 2. So we proved that Bn is equal to Bn minus 1 plus Bn minus 2. Okay, so we'll be solving the second subpart of the fifth question now. So essentially, essentially we have to prove that a to n is equal to a and bn. Let's play with the equations a bit. So we get a to n is equal to an into an plus 1 plus an minus 1. We can write an also in terms of an plus 1 and an minus 1 as an plus 1 minus an minus 1 into an plus 1 plus an minus 1, which is equal to an plus 1 square minus an minus 1 square. So essentially what we get is that a to n is equal to an n plus 1 square minus an minus 1 square, right? Now let's take the previous equation again. So we get a to n is equal to an into an plus 1 plus an into an minus 1. We essentially just expanded this equation, right? And then if we substitute the value n plus 1 instead of n, we get a into 2n plus 2 is equal to an plus 1 into an plus 2 plus an plus 1 into an, right? Now, if we subtract 8 1 from 8 1 plus 2, we get a2n plus 1 is equal to an plus 1 into an plus 2 minus an into an minus 1. Why do we get this? Because a2n plus 2 minus a2n is a2n plus 1 by the definition of Fibonacci sequence, right? So we get a2n plus 1 is equal to an plus 1 into an plus 2, which is this term right here. The term an plus 1 into an gets cancelled by this term, and we have minus an into an minus 1. Now we can write an plus 2 as an plus 1, this an plus 2 as an plus 1 into an. So we have an plus 1, an plus 1 plus an minus an into an minus 1. So this gives us an plus 1 squared plus an into an plus 1 minus an into an minus 1, right? And now if we write this an plus 1 as an plus an minus 1, so we get an plus 1 squared plus an squared plus an into an minus 1 minus an into an minus 1, and these two get cancelled. So essentially what we get is a2n plus 1 is equal to an plus 1 square plus an square. So what we'll be doing is we'll be proving both these equations by induction. So let's take the base case. So for the base case, we will take n equal to 2. So for the first equation, we will have a4 is equal to a3 square minus a1 square, right? Now we know that a4 is equal to 3. So 3 is equal to 2 square minus 1 square, which is true, right? And for the second equation, we get, when we substitute n equal to 2, we get a5 is equal to a3 square plus a2 square, right? And we know that a5 is equal to 5. a3 is equal to 2, so 2 square plus 1 square, which is also true. So for both the statements, the base case is true. Now for the induction hypotheses, let's say that both the equations are satisfied for all natural numbers n. For all natural numbers n that are less than k plus 1, which means that it satisfies for k. So let's substitute n equal to k. So we get a2k is equal to ak plus 1 square minus ak minus 1 square, and we have a2k plus 1 is equal to ak plus 1 square plus ak square. Now essentially what we have to prove that a2k plus 2 is equal to ak plus 2 square minus ak square, and a2k plus 3 is ak plus 2 square plus ak plus 1 square. If we prove these statements from these two statements, then we will have proved the inductive step, or the induction. Then we'll have proved the inductive step. So let's add both the equations. So we get a2k plus a2k plus 1 is equal to 2ak plus 1 square plus ak square minus ak minus 1 square. Now this a2k plus a2k plus 1 is essentially a2k plus 2, and we'll add and subtract ak square, and we'll also add and subtract 2ak into ak plus 1. So we have 2ak plus 1 whole square plus 2ak square plus 2ak into ak plus 1 minus ak minus 1 square minus ak square minus 2ak ak plus 1, right? Now this, we can take 1 ak plus 1 square, 1 ak square, and 2 ak into ak plus 1 to give ak plus 1 plus ak whole square. Then we can take one of these, one of ak plus 1 square, one of ak plus is ak square, and the minus 2ak into ak plus 1 to give ak plus 1 minus ak whole square. And then we have minus ak minus 1 square minus ak square, right? So by Fibonacci, this is essentially ak plus 2 square plus ak minus 1 square minus ak minus 1 square. This is ak minus 1 because ak plus 1 minus ak is equal to ak minus 1. And then ak minus 1 square minus ak square. And then we have a2k plus 2 is equal to ak plus 2 square minus ak square. So we have proved the first statement that we needed to prove. For the second statement that we need to prove, we will just add this equation and this equation. So we get a2k plus 2 plus a2k plus 1 is equal to ak plus 2 square minus ak square plus ak plus 1 square plus ak square. By Fibonacci, this gives us a2k plus 3 is equal to ak plus 2 square plus ak plus 1 square. Hence, we have proved the statements that were required to prove by the principle of mathematical induction. That is, a to n is equal to an bn, or in other words, a to n is equal to an plus 1 square minus an minus 1 square. Okay. So now we'll be solving the third part of the fifth question. We need to prove that b1 plus 2b2 plus 4b3 till to the power n minus 1 bn, the summation, is equal to 2 to the power n into a n plus 1 minus 1, right? So we will again prove this by induction. So let's take the base case. Let's say base case is n equal to 1. So for the LHS, we will have B1 is equal to, and for the RHS, we will have 2 into A2 minus 1. We know that B1 is equal to 1, and we also know that A2 is equal to 1. So we get 1 is equal to 2 into 1 minus 1, which is equal to 1, which is true. So the base case satisfies. Now for the induction hypothesis, let's say this is true for all natural numbers n less than k plus 1. Right, so let's substitute n equal to k. We have b1 plus 2b2 to the power k minus 1 bk is equal to the power k a k plus 1 minus 1. Right, now for the inductor step, let's add to the power k bk to both sides. We get b1 plus 2b2 plus till to the power k minus 1 bk plus to the power k bk plus 1 is equal to the power k is equal to the power k ak plus 1 plus to the power k bk plus 1 minus 1, right? Now the RHS is equal to the power k ak plus 1. We take to the power k common, so we have ak plus 1 plus bk plus 1, right? And then minus 1. If we expand bk plus 1, we get to the power k ak plus 1 plus ak plus 2 plus ak, yeah, that's ak, and then minus 1, right? By definition of Fibonacci, we know that ak is equal to ak plus ak plus 1 is equal to ak plus 2. So we get 2 into ak plus 2 minus 1, which is equal to 2 power k plus 1 ak plus 2 minus 1, right? So essentially we have proved that b1 plus 2b2 till 2 to the power k bk plus 1 is equal to the power k plus 1 ak plus 2 minus 1. This is basically the proof of the inductive step. So if it is true for all natural numbers n less than k plus 1, then it's also true for k plus 1. And hence, by principle of mathematical induction, we can say that the statement is true for all natural numbers n.